So last time we talked about wave packet decomposition and the uncertainty principle, and we talked about how we're sort of in the middle of saying that, okay, using wave packet decomposition, we get this sort of lemma that follows this sort of halfway estimate that follows from sort of looking at how much do two sort of transverse tubes intersect. And then today I said that, okay, how does this estimate imply the key estimate for the parabola? Okay, so let me review up to that point. So we have wave packet decomposition. Okay, and where some people call it the uncertainty principle, some people also call it the local constancy property. It goes by a bunch of names. They're all slightly different, but I'll call them all the same thing. Okay, so we're going to let I be an interval of length 1 over r, and let's say I is in 0, 1. Okay, and suppose G is Fourier supportive in the piece of parabola that lives above I. In P, which I'm going to call this region, okay. And then we're going to let Ti be the tiling of R2 by, so I'm going to write down all these definitions first, and then I'm going to draw the picture, and then you don't need to look at the definitions anymore. Okay, let Ti be the tiling of R2 by translates of this tube, I'm going to call T naught. Okay, it's the r by r squared tube pointing in the direction dual to that, so I'll draw a picture in a little bit. And so this is by translates of this, and T naught is the tube dual to P, and A is, say, the left endpoint of I. Okay, so let me draw what I even just defined. Okay, so I is an interval. I here, I is of length 1 over r. What's P? Well, it's a 1 over r by 1 over r squared neighborhood of the parabola inside 0, 1. This is basically 1 over r. This is 1 over r squared. Okay. To each I, okay, there's a point A. That's the left endpoint. This is not so important. You could literally pick any point inside this interval. Okay. There is, if you lift it to the parabola, there is a normal direction. Okay, it's 1 comma minus 2a. And then what's T naught? I take this direction, and I formulate the dual direction, the dual tube. It's an r by r squared tube. It's really a parallelogram if you actually draw it carefully and plot it out. It's really a parallelogram, but I mean, we can just dilate it slightly, and we just say it's r by r squared. Okay, it's an r by r squared tube centered at the origin. This is called T naught. This is P. And then what's T of I? T of I is, well, I can tile R2 by translates of this T naught. Okay, so that's everything that's so far. And what did we talk about last time? Well, we talked about that if G has Fourier transform supported in P, then absolute G is essentially constant on any translate of T naught. And this was sort of because of some slight cheating because of the phase heuristic. If you just write out what G is, you write out what G is, and then you say, okay, well, is it constant on T naught? Well, then you look at the e to the 2 pi I of stuff, you realize that the inside, as long as I'm inside one of these translates, then the e to the 2 pi of stuff is small, and that constant you get will depend on the particular translate of T naught, the function g, the thing p, a, and depend on everything, but nonetheless it's constant. So let me write out the heuristic. So then, okay, 1, absolute g is essentially constant on any translate of T naught. And of course, if you work in QP rather than R, this essentially constant is just really rigorously true. It's actually constant. Okay, this is using the phase heuristic. 2, absolute G is essentially constant on any ball of radius r. Where did this come from? Well, we take a ball of radius r. Remember, we don't distinguish between balls and squares. Okay, any ball of radius r, we can fit inside one of a translate of a T naught. Right? Because we don't also distinguish between 2r and r. Okay, there's a big O of 1 dilation of these guys that encapsulates this ball of radius r. And then, so since absolute G is basically constant on this tube, then it's basically constant on this ball. And then 3, there exists constant CT such that the absolute G, let's be slightly, is basically acts like a linear combination of these tubes. Okay, so, and that comes from the fact that, well, if I tile R2 by translates of T naught, all directions, it's a constant on each one of these tubes. So then I can write this. And why is this useful? Well, this is some stuff about Furry analysis, and this turns into a linear combination. And this turns into data about indicator functions. Right? And so then we start turning this problem about Furry analysis into sort of more combinatorial nature. Right? So what did we use this to prove last time? So we used this to prove the following. So last time I mentioned, so you know, in earlier lectures, when I talked about proof of decoupling for the parabola, I gave a very easy short proof of the key estimate that followed from Plancherel. And then last time, I talked about giving a proof of that key estimate in the style of Morgan and Demeter. In other words, using some sort of Kakeya type geometry. Right? And so this is the estimate that so right now we're just talking about the Morgan-Demeter style proof of that key estimate. It's not the key estimate they prove, but it's that you take the key estimate that I have, and then if you want to prove it in the style of Morgan and Demeter. Okay. Yes.
So I wondered if we can compute that CT.
You can, because you can work out what absolute value G is on each of these tubes, but it doesn't really tell you any data that way.
Also, you mean that our particular value is not important?
Yeah, the particular value is not important. You actually almost never care about what CT is.
Yeah. So I think we also cared about it small L to no.
Not quite. No, your proofs generally don't really touch what CT are. It's just that there exists some non-negative constant CTs. Because this constant CT will depend on G, it will depend on P, right there, it'll depend on which translate, and you can write it out. I mean, it's some oscillate e to the 2 pi times an integral of G times something, right? And of course, this is also heuristic, right? Rigorously, when you do this, remember, as I mentioned last time, one way to rigorously do this is to not work with G itself, but to work with G convolved with a sort of function that is about 1 on T naught and decays polynomially outside, and you'll realize that it's essentially, it's truly essentially constant up to a multiplicative factor. And you can write out what these constants are, but they don't really matter in the proof. Yeah. So that's the rigorously. And of course, I mentioned last time this needs to be L1 normalized, and then the integral of this is the integral of G. So that's one way to get around it. Or you can work in QP, and then you can literally exactly write out what CT is. Yeah, but you don't really touch the value of CT. You just know that they exist. There's some non-negative number, and they shouldn't rely on the fact that CT is at least 5 and no more than 10 or something, right? Of course, another way to construct a G is to pick CT, right? You could say, well, like, I'm 5 here and 1 here and pi here. Okay, and then that's one particular possible thing for G. Right? To construct examples, it's useful to pick coefficient CT, but when you do the proof of these things, it should not matter what CT is. Okay. So what did we use this decomposition to prove? So if I and I prime are such that I prime is nu to the b, and they have some separation, then the average value of this guy, right? We were considering these sort of bilinear expressions in this key estimate that we were proving, is bounded by nu to the minus bounded, where nu is a number that's large compared to delta but small compared to 1, times by this expression over here, this L2 norm times this L4. Okay, and what was the proof of this? Well, the proof of this was basically, so what did we do? We said, well, let's use wave packet decomposition. This breaks it up into a sum of tubes. These tubes are disjoint. And so the key geometric observation, okay, and then, okay, and, sorry, for all squares of side length nu to the minus 2b, okay. And the key geometric observation is that if this is a square of side length nu to the minus 2b by nu to the minus 2b, okay, the tubes corresponding to f theta I, let's say, point in this direction. Okay, these are nu to the minus b by nu to the minus 2b tubes. And the tubes corresponding to nu to the theta I prime point in a different direction. Okay, nu to the minus b also by nu to the minus 2b. The fact that I'm separated by a distance nu, right, so if you can imagine, let's draw the picture. So this is I prime. Okay, this is at least a distance nu. Okay, these tubes sort of point in this direction, these tubes point in this direction. Okay, since they're separated by a distance nu, what does this tell me about the angle? Well, that means it tells me that the angle is at least nu. Right? And then of course it's high school geometry to compute the intersection. Right? Because you see, if let's imagine that, f theta I was just one tube. Let's say just one tube. Right? Let's imagine a miracle happens and all the CTs were 0 except for one guy. Right? All the CTs were 0 except for this guy. And then for f theta I primes, all the CTs are 0 except for this one guy. Right? So then the left-hand side is basically counting how big is this intersection. So you can compute that. And if you compute the right-hand side, well, this is the average, a miracle happened. This was just one tube. You could easily compute. This is the volume of a tube. And this is the volume of another tube. That's essentially 95% of the geometry. Right? And then you could now add in coefficients. You use the fact that your tubes is a tiling. So, absolute, I forgot this. Absolute f theta I squared is just some ct squared times the indicator function of t. Right? And then you use this geometry calculation to basically compute that both sides are the same. Yeah. Okay. So where we stopped was saying, how does this estimate, so where we stopped, how does this estimate imply this estimate? Oops. Where's the eraser? how does this sort of Kakea estimate imply this estimate over here, which was the key estimate for that we used to prove decoupling for the parabola. Okay?
You also want two integrals over here?
No, there's only one integral. Yeah. Yeah. So basically the point is that the f theta I primes appear on both sides, and then the f theta I has decoupled into length nu to the 2b in L2. And yeah. And so last time, well, when we showed the first proof of this estimate, we showed that it basically followed from Plancherel. Right? We use the fact that this is a 2 here, we merge this in, and then we look at the Fourier transform of these f theta j's convolved these guys. Okay, and then, well, I mean, first thing we assume that this is at the origin. Okay, and then we said this follows from Plancherel. Now we're going to give a sort of Bourgain-Demeter style proof of this estimate. And yeah. Are there any questions? Okay. So, great. So let's try to prove this. We now have this estimate, and let's try to prove this estimate. Okay. So to prove this estimate, it suffices, of course, to prove that I don't have to prove it for all of R2. I just partition R2 into squares of side length nu to the minus 2b, and I just have to prove it for each square. Right? To prove, let's call this 1, and let's call this 2. To prove 2, suffices to show for each box of side length nu to the minus 2b, the integral of box of these guys Okay, it suffices to show this, because once I have that, I just sum both sides in box. And of course, it doesn't hurt if I just average, right? So if I could prove this guy, then I get rid of the average, sum in box, and then I get 2. Okay, great. So then at least I have the left-hand side in 1. So it just needs to show that this integral over here is less than this guy. Okay, remains to show that the average integral of this guy and the average integral of this guy is bounded by the sum in J times the average integral of this guy. And it's actually important. So you may ask, why am I not doing any different, larger or smaller squares? Right? Why this scale? Right? And it's this scale because I and I prime are a length nu to the b. That means they're dual boxes. What are their size of the dual boxes? Where does the action happen? The dual boxes happen at scale are of size nu to the minus b by nu to the minus 2b. Right? So f theta I prime, or f theta I prime, they basically look like things of size nu to the minus b by nu to the minus 2b. So to capture that data, you need to work on squares of size nu to the minus 2b. If you work on squares of too small length, then you're not capturing, let's say f theta I looks like this, and you work on a small box, well then you're only capturing part of the data. And if you're working on squares of size too big, like let's say this is a huge box, well then you're capturing too much data, you're not seeing enough of the fine scale. Right? So the right scale to pick is the size that's dictated by the wave packets. Okay? Okay, so why is this true? Well, if you imagine the fourth power wasn't there, right? This is almost like it almost wants to be like Plancherel. If you imagine there was no box, and if there was no fourth power, you could imagine that, okay, well, it's probably just Plancherel. And it's still just Plancherel, except with a little bit of tricks. Okay, so I actually want to keep this fact. Let's copy it here. And you don't need to write this. I just want to move this here of radius r. Okay. Okay. So let's first. So we just need to show this, and then that shows 2. Well, that shows this guy, which then shows 2. Okay. Okay, so we have the following lemma, which just follows from Plancherel it follows from Plancherel after one step. Some people will also call it L2-L2 decoupling, which if you also think for a little bit is also just Plancherel. Yeah, so if you read paper, some people will say, oh, by L2-L2 decoupling or stuff like that. Some people will also say by Plancherel. Okay, so what is the statement? Well, the integral over box of f theta I squared is bounded by f theta j squared. Okay, so if there is no box, this is truly Plancherel, because what is this saying? Well, this is saying, here's my I, and I'm breaking this up into little pieces of size nu to the 2b. And so you imagine my function is supported on the thickness of this chalk. And so what's the L2 norm? Let's imagine there was no box for a moment. Well, then what do? Well, I want to take a Fourier transform, right? And then f theta I hat is supported on these guys. Right, so if there was no box, I'd say f theta I hat squared. Right, and so then this is sum j f theta j hat squared. Right, and then well these are all disjoint, so I can bring the absolute in and undo the Fourier transform. Okay, so now what about this box? Right, how do we? It's almost the same proof. Okay, so this is the easy case. Okay, it's the same guideline, but now we have to add a little bit more complication. And that now we have a box, and of course this is where we're also slightly cheating. To make this rigorous, you can put a sharp cutoff here, but in the rigorous version, this needs to be a Schwartz function that's adapted to box. Okay, but I mean, since we're doing hand-wavy things, we'll just keep it like that. Okay, so what's the proof? It's almost this proof that I just wrote. So proof. Okay, so now we have a box. Okay, so box, let's write it. Let's still do it. Okay, well, what is this? Well, it's a box. So let's write sum j. J is of length nu to the 2b in I, times the indicator function of box, f theta j. Okay. Great. Okay, so now it's truly an L2 norm, so I can take a Fourier transform. When I take a Fourier transform, I add a convolution. Right? Okay, so now let's be a little heuristic, because this is really a sinc function. But let's imagine we had a Schwartz function adapted to box. Okay. Well, what is the Fourier transform of the indicator function of box? Okay. So since box is a square of side length nu to the minus 2b, what is this guy? Well, you can compute it. And if you compute it, you see that this is essentially supported on the ball centered at the origin of length nu to the 2b, maybe with some oscillation. But that's fine. We just care about the support. Okay. And so what do these guys look like? let's go back to the picture. Let's say this is my interval I. This is my interval j. Okay. J is of length nu to the 2b. Right? And now what I've done is I've convolved this piece of the parabola with a ball of radius size nu to the 2b. So what does this do to this function? Where's this function supported? Well, it's supported in sort of this football-shaped neighborhood, right? Still of size nu to the 2b. So this is the support of this guy. Right? I mean, I've basically just taken a ball and blurred it a little bit. Fine. But, you know, maybe it's of length like 10 times nu to the 2b now. But that means as j varies, these little footballs are all finitely overlapping. Right? And then finitely overlapping, well, that's fine. I use enough Cauchy-Schwarzes. Finitely overlapping, I can move the absolute value inside, and that's why I have a little tilde here. So I lose maybe a constant of like 100 or something. Okay? Are there any questions with this proof? Okay, great. So we're slowly getting there, right? So we have this guy, which is an average. Now I can already see the sum appearing, but I still have two integrals. How do I get rid of one of them? And then here's where we do something, well, here we're going to use the uncertainty principle. Okay, so we remain to show this. Okay, so then by L2, L2, okay, we just need to show we have, so the average integral of f theta I squared, average integral of f theta I prime to the 4. What did we just have? Well, we have that this is less than the sum over j times the average integral of f theta j squared times the average, of course, and then this is times the average integral of f theta I prime to the 4. Right? So right now what we have is that this left-hand side is less than this guy over here. Right? I can just add in the averages. This right-hand side over here times by this guy over here. Okay? So now we arrive at the question. So what is the last thing we need to show? We need to show why is this term over here bounded by this term. Okay? That's the last thing we need to show. So now we slowly reduce and we ask a question. Why is the integral box f theta j squared, f theta I prime, oops, there are two of them, f theta I prime to the 4, bounded by the average integral of f theta j squared, f theta I prime to the 4. Okay, and here we really need to use the fact that this is nu to the minus 2b, this is nu to the 2b scale. Okay? Great, so I have two integrals on the left and one integral on the right. What just happened? Okay, so now let's now use the uncertainty principle. And it does need proof, right? So, okay, great. So let's go back to this statement over here, and let's remember. So g here is now f theta j. Okay, g here is this function. Okay, p is theta j. Okay, so absolute g, so in other words, absolute f theta j is essentially constant on any ball of radius r. What's r in this theorem? R is nu to the minus 2b. Okay? Because that's the inverse scale of this j. So f theta j absolute value is constant on this box. It's like 5. Okay? So if this guy was 5, I could bring 5 inside this integral here. Okay? So this guy, by the uncertainty principle, okay, this is uncertainty principle. This is equal to the average value of some constant that depends on, maybe j, box, theta, okay, and so on and so forth, times by f theta I prime to the 4 squared. But that's exactly what this does, right? The value of f theta j on this box is c. The value of f theta j squared on this box is also c. So this is actually equality. Right. Are there any questions about this step? This is the most, I'd say probably the most cheating step. But this is the trick to use to get rid of two integrals. Yeah. In fact, this is an equality in the sense of this. And so, yeah, I mean, you have to make this rigorous, right? This is not just inserting Schwartz functions and hoping for the best, right? But under the uncertainty principle, this is sort of true. And once you have an uncertainty principle-based proof, then it suggests that there is a way to make this rigorous. And you can go look at the study guide for one way. You can also make it rigorous by working with not absolute g, but absolute g convolved, a certain Schwartz function that's adapted to t naught, and so on and so forth. Or you can just work in QP, and then this is literally true. Yeah. So this is the proof of the key estimate in the style of Bourgain and Demeter, where then they need to use some sort of Kakeya type estimate. Okay, and the buzzword, if you read their papers, is called ball inflation. Or if you read the paper that I wrote called, what's it called? A decoupling interpretation of efficient congruencing, something like that, for the parabola. This is somewhat of an analog of their Bourgain and Demeter ball inflation lemma, and then you can use it to prove this key estimate. Bourgain and Demeter sort of use, instead of 2 plus 4, they sort of use 3 plus 3. But they also need to use this Plancherel L2L2 decoupling. So they have a slightly more complicated bilinear object to handle that. Yeah. Okay, are there any questions? So now I've given you 2 proofs of this, and if we have time, I'll even give you a 3rd proof after I talk about the number theory stuff. Okay, so hopefully you're fairly convinced that this is true, since I've given 2 proofs. Yeah. Okay. Are there any questions? So now we're going to move to, I came up with this proof in 2018. Of course, it's been, the first proof was actually Terry Tao taught a class, I think, at the beginning of the pandemic, at least in the US at the beginning of the pandemic. The first proof that was just Plancherel and strips was first written out in his lecture notes. But more or less, it is more or less the same proof that I wrote in the paper in 2018, and then the proof in the paper in 2018 also includes this proof. But where did this proof come from? So let's try to explain where did this proof come from, or what. So this proof came out of trying to study sort of this resultant number theory called Venerata's mean value theorem. So let's see, how should I explain this? So let's just start from the beginning for Venerata's mean value theorem. What is Venerata's mean value theorem? And then eventually I'll mention what inspired me to come up with even trying to prove such a thing. Okay? I mean, because, this is not a natural analysis estimate to do, I think. I think for, what says to weight this by 2 and weight this by 4? I mean, I think the more natural combination to do is 3 and 3, right? But there is a number theory motivation as to why one puts 2 and 4 here. Okay. So let's start from the beginning, and so for the rest of the lecture, I'm going to mention number theory and sort of what led me to come up with these estimates, and how does this estimate connect to number theory. Okay. Okay. So what's Venerata's mean value theorem? So this proof came out of me from studying Venerata's mean value theorem. So what's Venerata's mean value theorem? And this will also be a very brief history because the history of that conjecture is also very long and lots of people. So we're going to let JSK of x be the number of solutions to, okay, let's say number of 2s tuples. Number of 2s tuples that are solutions to x1 all the way to plus xs equals y1 plus ys, x1 squared, xs squared, y1 squared, ys squared. And we go all the way down to x1 to the k, xs to the k, y1 to the k, ys to the k, where all the variables lie between 1 and x. Okay? Or any interval of size x. Okay, so one can ask, how many solutions are there to this? Okay, so Venerata in 1935 had some applications in mind to estimating Weyl sums, and he was the first to give a sort of upper bound for the number of solutions. And then Hua in 1941, or in I can't quite track who came up with the word Venerata's mean value theorem. Certainly not Venerata. That would seem very arrogant. I believe Hua came up with the terminology Venerata's mean value theorem. I kind of suspect in 1941. But there was sort of a game. You know, what's the best upper bound you can prove for this system? Okay, for all s and k. Okay, of course, if you have s be k, right? Let's say we have k variables on both sides. Then I'm just going to pick y1 to ys randomly. Then we know from, you know, if one did some Olympiads, right? If I know what, let's say, a plus b plus c is, and a squared plus b squared plus c squared is, and a cubed plus b cubed plus c cubed is, you know exactly what a, b, c are, right? This is the Newton identities, right? So, you know, if s is k, that's great. But, you know, you want all k. Or if, let's say s is 2, that's also even obvious, right? Small k is generally easy up to a certain point. And then you sort of want the estimate for all k. So let's think about what's a lower bound for JS. Okay. So what's a lower bound? Okay, so there's the obvious lower bound, where I just let x1 be y1 be anything, x2 be y2 be anything, all the way to xs be ys be anything, right? So how many solutions does that give? So the diagonal solutions give x to the s many. And I'm going to ignore all constants and, you know, whatever. Okay, so what's another potential contribution? So I'm going to call it the random contribution. This won't be a rigorous proof, but you can make it rigorous using different methods. But this is how you remember the numerology. So I'm going to call the random contribution. Some people will call it the dimension counting argument. So random contribution. So let's imagine x1 to ys are randomly between 1 and x. Okay? That gives me x to the 2s many chances, possibilities. Okay, so what's the probability that the first equation is satisfied? Well, if x1 and y1 range between 1 and x, this is between like minus sx and plus sx. Right? If you imagine that this inequality is basically saying x1 plus xs minus y1 minus. Right? The value of this is a number between minus sx and plus sx. So if a random 2s tuple satisfies this equation, what's the chance that this expression over here, so for each random 2s tuple, I compute this guy. It's a random number between basically minus sx and plus sx. What's the probability it equals 0? Well, it's a 1 in x chance, ignoring the s. It's a 1 in x chance of happening, right? Similarly, what's the probability that if I have a random 2s tuple over here, I compute this guy minus this guy, What's the probability that that's equal to 0? Well, heuristically, we should think that's a 1 in x squared chance of happening. Right? And what's the probability of all these? Well, this is a 1 in x cubed, 1 in x to the 4, all the way down to 1 over x to the k. Right? So probability has a 1 over x squared, 1 over x to the k. Okay. Of course, this is all heuristics, right? None of this is rigorous, but trying to how one should think of these. Additionally, if I satisfy the linear equation, there's no real reason why I should satisfy the quadratic equation in general, and there's no real reason. There's no algebraic conspiracy here. Right? The linear equation should be satisfied independent of the quadratic equation, etc. So these are all independent events. So if I take a random 2s tuple, what's the probability I satisfy the whole system? Well, I just multiply the probabilities. Right? So another contribution is x to the 2s. There are this many 2s tuples minus 1/2 times k plus 1. Right? And you can make this rigorous by looking at the exponential sum and looking at where the peaks are. But this is how I remember the numerology. Okay. Or this is also how you do the back of the envelope calculations to see how many solutions you should have. Right? There are almost, there are going to be 2 contributions, one from the diagonal and one from sort of this random heuristic. Okay. Great. So the lower bound is should be that jsk of x is at least x to the s plus x to the 2s minus half k times k plus 1. Okay. Great. Well, what should one conjecture the upper bound be? Well, it'd be nice if the upper bound was not much more than the upper bound. Right? So, what's the conjecture? The main conjecture in Venerata's mean value theorem is that jsk of x is bounded by epsilon sk x to the epsilon times x to the s plus this guy. Okay, so what does this main conjecture say? It says that the number of solutions is not much more than the lower bound. Right? There's only an x to the epsilon. There are stronger versions of this conjecture in that there are people who believe that the only time where the x to the epsilon happens is when s and k are 3 and 2. That's a bit strong. And there are certain regimes where you can get rid of the x to the epsilon, actually. Okay, so this is a theorem. So this is a theorem for various cases. So let's before we talk about when. So this is a theorem. Okay, I'll just say that. This is a theorem as of 2015, but partial cases have been proven slightly earlier. Okay, so great. What did I want to say next? Okay, so where's the Furry analysis? Okay, so how does this, I'm just solution counting here, so how does this lead to Furry analysis? Well, of note that since e to the 2 pi x times n, okay, this is a true identity, right? Then jsk of x, what is this? Well, this is just this guy. Right. So, and to see the d alpha, to see that the number of solutions is equal to this, well, you just take the 2s as an integer. Okay, remember e of something is, the notation is e of z is e to the 2 pi I times z. Okay, so to see this, well, we expand the 2s power. 2s is an integer, so we expand it. We get a giant sum, swap the integral and the sum, and use the fact that the integral of e to the 2 pi x times n is the indicator function of n being 0. k is 2, that's the right one. Okay. So why is it called the mean value theorem? Well, it's just, what's the mean value of this exponential sum over the unit cube. Right? So that's where the term mean value comes from. Okay. So that's where, if you look here, like, where is it called the mean value? Well, it's because everyone attacks this problem by trying to estimate LP norms of this exponential sum. Okay. Okay. So, what does the conjecture turn into? Well, then it says the L2S norm of this exponential sum is bounded by that right-hand side. Okay, by 2 terms. And so by interpolation, so you can imagine you can compute the L2 norm when s is equal to 1. You can also compute the L infinity norm. Right? The L infinity norm is just, imagine at the origin, you can compute the L infinity norm. And if you use Holder, you interpolate between L2 and L infinity, it suffices to only show the case when s is, or when 2s is k times k plus 1, or in other words, when the 2 powers match. Okay? So I'll leave that as a little exercise, but let me write that down. So, okay. Main goal is to show that the yeah, okay. And then what you can do is Holder, interpolation with L2 and L infinity shows that it suffices to show the case when these 2 powers are equal. Or you can think that, well, you have 2 terms. If you set them equal, then that's something where something special should happen. Okay, and it turns out if you interpolate correctly, that's indeed correct. And 2s minus half k times k plus 1 is equal to s, or in other words, 2s is k times k plus 1. Okay. And it's not a fluke that when k times k plus 1, what happens when k is 2? Well, that's when 2s is 6. That's an L6 norm. Right, and that's exactly the critical exponent for the parabola. Okay. Okay, so what's the history of Venerata's mean value theorem? Well, this is a very, very brief history. In fact, it's missing a lot of names. This is almost like the top line summary of the history of the resolution. There have been lots of partial results, but I could write down a whole board of names if I were to do that. So let's mention the top line results. So it suffices to prove the L2S estimate for this exponential sum for each k. As long as you can obtain, so when k is 2, as long as you can obtain the L6 estimate, you've solved the k equals 2 estimate. Right? As long as you can obtain the k equals 12, the k equals 3 estimate, which is when the L12 estimate for when k equals 3, you've solved the k equals 3 problem. Okay. Now, of course, people, historically, as the theory developed, people weren't able to get the critical exponent. They were able to get maybe, either bigger LP estimates when p is bigger than this estimate, or stuff, and so on and so forth. Let's summarize the top line. Who resolved what? So when k equals 2, this is classical, actually. The reason is because, when k equals 2. Let's even just delete all this. So we're only looking at the top line here, and you only need the critical estimate is when s is 3, or in other words, 2s is 6. Okay, 3 variables on both sides. Well, and then there are some algebraic identities relating the quadratic thing and the linear thing, and it turns out to follow from the divisor bound. Okay? Okay, so k equals 2 is classical. Okay. K equals 3. So this problem was first solved, first stated by, considered by Venerata in 1935. So when was the k equals 3 estimate proven? Well, the k equals 3 case was proven by Woolley in 2014. So that's about 79 years. Using efficient congruencing, this method of efficient congruencing that I'll hopefully have time to introduce. Right, and in 2015 there was a simplification with simplification by Heath Brown in 2015. So Woolley wrote not a super long paper, but it's not super short either, proving the k equals 3 case. That was the L12 estimate in the analysis language, the L12 norm of this exponential sum of k equals 3. And then in 2015, actually right around the time when Bourgain, Demeter, Guth came out, Heath Brown posted a simplification of this efficient congruencing proof. Okay, so that's k equals 3. And then in December of 2015, okay, so in December of 2015, the general k bigger than 2 case was solved. So December 2015, these are all the archive dates, rather than the published dates. So the k equals 2 case proven by Bourgain, Demeter, and Guth, Larry Guth, using as a corollary of L2 Lk times k plus 1 decoupling for the moment curve. And remember, when k is 2, this is 6, right? So, and this turns out to be the sharp exponent, right? Okay. And then, okay, great. So, up previous work, there had been previous work in certain regimes of S and K. They're all considering the number theory language, right? They're all in the direction of efficient congruencing and stuff like that. And then in k bigger than or equal, and then in December 2015, Bourgain, Demeter, Guth showed that this problem is not a number theory problem, in some sense. It follows from a harmonic analysis decoupling argument. Okay? Now, one can ask, well, can you still use this technology, this number theory technology, to prove Venerata's mean value theorem? And the answer is yes. So that in Woolley in 2017, k bigger than or equal to 2 proved by Woolley using efficient congruencing. And we'll talk about what efficient congruencing is even. Okay? So, in the time period after 2017, so this was when there was a what do you call it, a semester workshop thing at MSRI in harmonic analysis and number theory. So there were various conferences discussing, I believe even one at the Fields Institute, you have these two proofs, right? You have this decoupling proof of Venerata's mean value theorem that showed, really it's a harmonic analysis theorem. You write a function whose Fourier transform is supported in some thin neighborhood of the moment curve, right? The moment curve being C maps to C squared, C to the k. Okay, you can consider so remember how we did it for the parabola, right? Some thin neighborhood of the parabola. Well, you can imagine the same problem for a thin neighborhood of the moment curve. So we have this decoupling. We have this harmonic analysis proof that showed that, well, this problem is just a corollary of the decoupling for the moment curve. And then you have the number theory side of things where you showed that this problem is a consequence of some number theory things. Okay. Then people started asking, well, are these two proofs related? I mean, they all had some sort of iteration Okay, and so for example, one key tool that is used in all efficient congruencing proofs is that this system is quite special. Okay, this system is known as called the translation, dilation, invariant system. Well, it's dilation invariant because let's say I add a solution to this system, x1 to ys. And I multiply all the solution by 5. 5 times x1, 5 times x2, all the way to 5 times ys. That's also a solution. That's obvious. Okay. But more importantly, it's translation invariant. Right? So if I have a solution x1 to ys, x1 plus 1, x2 plus 1, x3 plus 1, all the way to ys plus 1. That's also a solution to this system. The reason is because, well, you just plug in x1 plus 1, x2 plus 2. Well, that's obviously satisfied. You plug in x1 plus 1, x2 plus 1, all the way to ys plus 1. You get a bunch of linear terms. When the linear terms are satisfied, you have the quadratic terms satisfied. And because you have the quadratic terms satisfied, the cubic terms are satisfied. You have all the powers. The binomial theorem tells you that translations of a solution is also a solution. Okay? So this system is special in the sense of its translation and dilation invariant. And what's the analog in the decoupling world? What's so special about the parabola that we use? Well, we use the fact that we have parabolic rescaling. We have this nice rescaling property. And similarly, there is a similar property. Can call it just affine rescaling. This similar property holds for the moment curve. Okay? Or if you want to just think in the parabola case that we've talked so much about, the parabola case also is a translation dilation invariant system. And in the parabola decoupling, we made a lot of use of parabolic rescaling. Right? These tools are linked. Right? There's some sort of rescaling property that we needed to sort of allow sort of dilations and translations of our system and to consider the problem at smaller scales or larger scales. Yeah. Okay. Let's see. So now, so we had two different proofs. There are a priori some similarity. Both proofs use an iteration. Okay. Both proofs have some sort of rescaling property. And then people started asking, well, how are these two proofs related? Okay. So the proof that I just presented, that I spent the last 3 lectures presenting, was inspired this way. So after these two papers were written, Lillian Pierce in her Bourbaki seminar notes wrote a sort of comparison between these two papers. And she also mentioned on decoupling side of things, we have a rescaling, and on these side of things, we have translation invariance. These should be related. And then at the end in section 8, she writes, okay, and then more should be explored. And then I remember reading that, I took that, okay, well, I should try to do this. And then so in particular in section 4 of her Bourbaki seminar notes, she writes the k equals 2 argument of, so I said that k equals 2 is classical. Of course, you could use efficient congruencing to prove the k equals 2 case, just as, Baby's first efficient congruencing argument, right? So in section 4 of those Bourbaki seminar notes, she writes the k equals 2 argument. And then it's that proof that inspired me to come up with this proof that I had just showed you. Okay? So I guess it's a good time to take a break, but when we come back from the break, maybe I first show you the k equals 2 argument for efficient congruencing, and then how that sort of translated into a decoupling argument. So then you can also see what is efficient congruencing and where does this decoupling argument even come from? Okay? And so I guess we'll take a little short break and come back in a little bit. About the k equals 2 case in efficient congruencing. But before we do that, let me just briefly remark how decoupling for the parabola implies Venerata's mean value theorem. Okay, just to wrap up that loose end. Okay, so for the rest of the talk, we talk about k equals 2. Okay, so question 1. How does L2, L6 parabola decoupling imply k equals 2 Venerata? Okay, so we know that the L6 norm of f is bounded by delta to the minus epsilon, sum I in p delta, f theta I, L6 squared 1/2, for all f Fourier supported in a delta squared neighborhood of the parabola. Okay, where, remember, theta I, so I is integral size delta. This is a delta by delta squared neighborhood. Okay, we spent a lot of time proving this. How does this imply J32 of x is less than x cubed plus epsilon? Right? So when k equals 2, so let's write this down. Okay, when k equals 2, the critical exponent was when 2s equals 6, so s is 3. What's J32? J32 is the number of solutions to this system where the variables lie between 1 and x. And of course, the conjecture, now theorem, is that J32 of x is bounded by x cubed, basically. In other words, the number of solutions in the system is basically the diagonal solution. Okay, so how do you do this? Well, I'm just going to write down what point. So this estimate is true for all f whose Fourier transform is supported inside the delta squared neighborhood of the piece of parabola above 0, 1. Okay. Let's draw a picture. Okay. So for all f whose Fourier transform lives here, I have this estimate. So I just need to pick an f. Right? Which f do I pick? So let me write that down. Okay, so we're going to take delta to be 1 over x. We're going to pick I to be the interval n over x comma n plus 1 over x for, say, n equals 0, 1 to x minus 1. And what function are we going to pick? Well, basically, let's draw a picture of the function first. 1 over x, 2 over x, 3 over x. And then we have the 1 over x squared neighborhood of the parabola. We're basically going to pick a Dirac delta spike at each of these points. Okay? So let's write it down. What function are we going to pick? We're going to pick f theta I x, y to be equal to the indicator function of a ball of radius x squared and x, y times by the integral over I times a Dirac delta spike at the left endpoint times this Fourier transform. And secretly, when I write a Dirac delta spike, you think it's a Schwartz function. Okay. And why is this function as Fourier transform supported here? Well, this is just the indicator function of 0x squared squared times by the Dirac delta spike evaluated at n comma x times by the indicator function of the interval times by the surface measure on the parabola for A inverse. Right? Of course, it's not quite the surface measure. Let's just take the measure on the parabola. Okay, and then the Fourier transform of f theta I, well, this is a ball of radius delta to x to the minus 2, right, which is delta squared. And then, well, this is supported on the measure. Right? So when I convolve it, it only gives me a little neighborhood. So this function is truly supported in a delta squared neighborhood of the parabola. Okay. And then once you compute this function, so I won't do this calculation, once you compute this function, so what is the Fourier inverse of a Dirac delta function? Well, it's an exponential, right? So if you compute this function, this is just the indicator function times e of nx times x plus n squared over x squared times y. And so if you plug this in to this inequality over here, and you do a bunch of change of variables, you'll quickly see that you're going to get the right-hand side when s is 3 and k is 2. So you do some change of variables. Okay, and you're going to get the right estimate. Okay? Are there any questions? You just pick some function. Basically, it's the Dirac delta spike at each point over here. Yeah. Okay. Great. So now the second question we're going to talk about is what's the k equals 2 efficient congruencing argument for this guy? How does the efficient congruencing argument work to prove this? Okay. So question 2, how does the k equals 2 efficient congruencing argument work to prove J32 of x is less than x cubed plus epsilon? Okay. So they also use a bilinear object. In fact, even when Woolley proves the general k case, it's also a bilinear argument, which is different from when Bourgain, Demeter, Guth proved their general k case. They use a k factorial linear decoupling argument. So if you want the most obvious difference between these two proofs, this proof uses at least a k. I think if you probably could get it down to k linear. They use one multilinear decoupling constant. Woolley will use k, or is it, I believe he uses k different bilinear objects, and they all sort of relate to each other. So that's one very clear difference between these two proofs. Okay. Okay. So of course, when k is 2, k factorial is the same as bilinear. So how does the k equals 2 argument work to prove their efficient congruency argument? Well, so they use a bilinear object, and it's called the following. So bilinear expression. Okay, they say, well, okay, so we're going to let p be a prime that's small compared to x and large compared to 1. Okay, should play the same role as nu plays. And we're going to let I of xab be this expression. So it's let me write it down first. So I'm going to actually have a residue class C mod p to the A and A to mod p to the B, and they're not congruent to each other mod p. And I'm going to consider this expression over here. Okay, so they consider this expression over here. So, what is this expression? Okay, so first, let's also keep in mind how big is this expression? So heuristically, how big is this expression? Well, if we should expect in number theory that things, if there's no reason why there should be extra cancellation, we should imagine at best it says square root cancellation, right? Square root cancellation. So if we imagine square root cancellation happen, how big should this be? Well, if we imagine square root cancellation happening, well then it's just, well, how big is this absolute value? Well, this absolute value should be the square root of the number of terms, which is x over p to the a, but then squared, okay? Or, so how big should we expect this to be? It should be x over p to the a, which is the number of terms, times 1/2 times 2.
So then how about, that means that the notation, what is the CP? What is the
Yeah, so I'm going to take a residue, so this is notation for C mod p to the a, right? So this exponential sum, you take two residue classes, C mod p to the a to mod p to the b, and you assume they're not congruent to each other mod p. Okay, and I could just compute this integral. And heuristically, we expect this exponential sum to be x over p to the a, which is the number of terms, to the 1/2, but then it gets squared. And heuristically, we expect this exponential sum to be like x over p to the b to the 1/2 times 4. So heuristically, we expect that this term should be x cubed over p to the a plus 2b. Okay, just to have oneself keep in mind how big this object is. Okay. Okay. So that's an integral. Okay. So what does it count? Okay, so what does this integral count? Well, this integral counts the following. So 1, what does I of x, a, b count? Okay. Well, it says the following. I mean, because, you could use the fact that the integral from 0 to 1 of e to the 2 pi of something counts the solutions, the number of something. So what does this integral count? Okay, so it says fix c mod p to the a and eta mod p to the b, where c is not eta mod p. Okay, the integral counts the number of solutions to the following system: n1 plus n2 plus n3 is n4 plus n5 plus n6, and the squares where all the variables lie between 1 and x. So far I've done nothing. This is just traditional Venerata for J32. But what do these constraints put in? Well, these constraints require that the n1 and n4 are congruent to c mod p to the a, and the other variables n2, n3, n5, and n6 are congruent to eta mod p to the b. Okay, so that integral says the following. I of xab says the following. Take a residue class c mod p to the a, eta mod p to the b, such that c is not congruent to p. Then compute this integral. This integral counts the number of solutions of this system where the first and fourth variables are congruent to c mod p to the a, the other variables are congruent to eta mod p to the b. And I is the worst one of these counts. Now, on one hand, you should expect the typical choice of, this exponential sum should not be biased over one residue class or another. It sort of says, take your typical residue classes that satisfy these conditions. How many solutions are there to this system?
So here the p is prime.
Yeah, p is a prime.
And so in the case because it's congruent eta not to p, which means there's no solution.
Wait, what do you mean?
I mean, what is it with the equal to eta?
because C is eta mod P?
You do the maxima because it's not equal to E eta mod P.
Yeah.
And in this case, because C equal to E eta mod P. What?
I mean, you could still have solutions, right? But this is the bilinear object. This is very similar to how, actually that's the second point I'll make. This is very similar to the idea that we have some sort of transversality in our f theta and f theta I primes, right? So let me write down the bilinear decoupling constant that we just had used, okay? So, okay, so that decoupling constant, or that bilinear object, the analog, IAB sort of inspired sort of the bilinear decoupling, MAB, that we had talked about. So what is that? So MAB is the best constant such that the integral of f theta I squared times f theta I prime to the 4 is less than MAB delta nu to the 6 times by I decouple I into intervals of size delta and I decouple I prime into intervals of size delta. And this is for all, okay, f with Fourier transform supported in the delta squared neighborhood of the parabola. Okay, well, let's not write that. For all I equal nu to the a, I prime equal nu to the b, and the distance between I and I prime is at least nu. Right? So and to end all. All f with Fourier support in delta squared neighborhood of parabola. Okay. How are these the same? Well, this is an exponential sum over a residue class mod p to the a. This is a function whose Fourier transform supported over an on the piece of the parabola over an interval of length nu to the a. Okay. This is an exponential sum whose exponential sum is over residue class mod p to the b. This is a p-adic interval of length p to the minus b. This is a function whose Fourier transform is supported in on the piece of parabola above an interval length nu to the b. Okay. And then furthermore, this over here is the maximum over residue classes that aren't congruent to each other mod. So c to the a, c to the b, these intervals are not congruent to each other mod p. That's the same as saying that these intervals, so p-adically, that's p-adic separation. Right? These are p-adically separated, and so this is separated by a length nu. Okay? So you can think that there's some sort of transversality. Of course, you could put the congruence class over C as congruent to eta mod P, but that would count something else, but we're not going to do that. We want to use this transversality. All right. So it's that choice, when I read Lillian's exposition on the k equals 2 case, I was like, ah, okay, well, this is a natural analog to 2 in decoupling. Right? Okay. Yeah. Okay. Are there any questions? Yeah.
So in that I, it is integrated in Q over QB, or in Woolley's paper, it is integrated over QB over.
No. Woolley will consider objects that this is just it's over the unit cube. Yeah. Yeah. This is a real integral. You can interpret these things in QP, but that's not done in that or over here. Yeah.
See that, I mean, you're now mod P.
Uh-huh.
But mod P is now, oh, okay. I mean, so you mean after mod P, it divided your original interval into small pieces? Since you want to method between these two.
I mean, the mod P is just some sort of separation in the p-adic language, right? I just have two residue classes, C mod P to the B, and they're not congruent to each other mod P, right? And so that's some sort of separation, right? Like if you imagine that 0, 1, okay, you chop it up into intervals mod P, okay, and okay, so now I have an interval length P to the minus A and of length P to the minus B. This condition says that they don't lie in the same interval, the same residue class mod P. And so that's, I mean, if you want to translate into the real language, that's exactly forces some separation to happen. Yeah. They don't have the same parent at scale nu. Right. Okay, great. So that's one thing. And what's the key estimate? So let's talk about the key estimate, because the rest, okay, I mean, there's the translation invariance, there's some holder, okay, there's some sort of reduction from J of 3, 2 down to this object. It's also just holder. So what's the key estimate in their world? Okay. Okay, so what's the key estimate in their world? Well, it will look very familiar. Oh, I shouldn't have erased that, but oh well. Key estimate in k equals 2 efficient congruency is that I of xbb is less than p to the b I of x to bb. So let's pause for a moment. If one wants to think immediately that IAB is MAB, and we want to think that P is nu, that's not so great, right? This is a nu to the, if we want to literally translate, right? Question, question, question. MBB is less than nu to the B, maybe minus B, times M to BB. Well, if you try to do this naively, well, this is not going to work in the iteration. Right? We really needed nothing here. Well, there's something you have to remember. MAB is the bilinear decoupling constant. What do we want for decoupling at L6 in the end? We want the decoupling constant is of size 1. Sure, delta to the minus epsilon, but up to delta to the minus epsilon, MAB should basically be of size 1 at the end of the game. On the other hand, what do we want in the efficient congruency world? We want J, where's my estimate? J to be basically x cubed, right? So we want decoupling to be of size 1, J to be of x cubed. So we need to normalize things in order to get the correct estimate to guess, right? So that explains why there's a P to the B here, because let's rewrite this estimate. We write this estimate as the follow. P to the 3B over x cubed times I of xbb is less than P to the 4B over x cubed times I of x2bb. Okay, slightly strange, but this is still true. And heuristically, we remember that I of xab is this size. So heuristically, this guy is of size 1, and heuristically, this guy is of size 1. And this is what led me to guess that, okay, well, mbb should be less than m2bb. Okay? And then, okay, you're like, well, I want to prove this estimate. What kind of estimate about these bilinear expressions would imply that mbb is bounded by m2bb? Well, then you get the key estimate that we just talked about in the parabola decoupling estimate. Okay? So that's how the thought process that led to the key estimate. Now, before we end, how is this proof, how is this expression proven? Okay? I'm going to mention how is this proven. And if I have time at the end, I'll give you a third proof of the quiescent for the decoupling parabola that looks closest to this proof. So now you'll see 3 proofs of the quiescent for the decoupling for the parabola in 3 different styles. Okay, so let's outline. Let's write down this proof, and you'll mention. So you see, the hard part of trying to see connection between efficient currency and decoupling is it's not obvious. Sort of, it's not like there's not like a ready-made dictionary where you just start copying. Right? You need to sort of take their proof. You ask, what is the key idea? And distill it down into sort of what is the key harmonic analysis idea? And you're like, okay, what is this in the real case? Okay. And this becomes an issue, especially in this solution, as you'll see, is that it relies a lot on solution counting. Okay. If I'm counting solutions, 1, 2, 3, 4, 5, what am I doing in analysis? It's not entirely clear. Okay. So let's prove this. Okay. Great, I want to prove that IBB is less than P to the B times I2BB. Okay, so I just need to show for every C mod P to the B, A to mod P to the B. Okay, so let's write down this. Okay, so it suffices to show, proof, it suffices to show that for each C mod P to the B, A to mod P to the B, C not concurrent to A to mod P, that the number of solutions to the system n1 plus n2 plus n3 is n4 plus n5 plus n6 and the square okay, and then the variables lie between 1 and x. 1 and 4 are congruent to C mod P to the A, and the 2, 3, 5, 6 variables are congruent to A to mod P to the B, or P, both of them are P to the B, sorry. I just want to show that the number of solutions to this is bounded by P to the B times this guy. Because this sentence exactly counts this integral when A and B are 1, and then I take a maximum. If I can show that this integral is bounded by this right-hand side, I take a maximum, well then the maximum is less than P to the B times I2BB. So what do we want to do? Well, so we want to show is less than P to the B I x 2BB. What are we doing here? We want to show what is I of 2BB? I of 2BB is the same sentence, except we've upgraded the n1 and the 4 variables from mod P to the B data to mod P to the 2B data. Okay? So what is the goal here? So this is the somewhat tedious thing of reading these proofs, right? Every one of these implies some solution counting, and they always work with the solution counting. Okay. So what do we want to do? I want to count the number of solutions of this system satisfying these equations. And I want to upgrade the 1 and 4 variables from mod P to the B to mod P to the 2B. And then the other variables, because I haven't moved this index over here, the other variables aren't upgraded. Okay? So that's the key goal. You don't have to remember what the terminology means. I just need to upgrade 1 and 4 up to mod P to the 2B. Okay, so how is that done? Yeah, sure. Okay, so I just need to look at n1 and n4 and upgrade it to mod P to the 2B. Okay. Well, this system over here is translation invariant. Right? If I subtract all the solutions by eta, that's also a solution. Okay? So by translation invariance, we may assume eta equals 0. Right? So now, The 2, 3, 5, 6 variables are all divisible by p to the b. They're all 0 mod p to the b. Okay? So now let's write the following. Write ni for I equals 1 and 4 as c plus p to the b ai. And for ni for I equals 2, 3, 5, 6, we're going to write, they're all divisible by p to the b, so we're going to write as p to the b times ai. We're going to do the typical elementary school thing we did. Okay. And we also know one more thing. C is not congruent to eta mod p. So that means C is not congruent to 0 mod p. Okay. Great. Now what's the next step we do? Well, the next step we want to try to do is plug them into the equation, right? Now, let's look at the quadratic equation. Great. So we look at the quadratic equation. What scale do we want to look at the quadratic equation at? What mod should we look at the quadratic equation at? Well, the 2, 3, 5, 6 variables are all divisible by p to the b, so all the squares are divisible by p to the 2b. So if we want to upgrade n1 and n4, we ought to look at the quadratic equation at scale mod p to the 2b. At least it's natural to do that, right? You wouldn't pick any other scale. So look at quadratic equation mod p to the 2b to get, okay, what do we get? Well, we get c plus p to the a1 squared is congruent to c plus p to the b a4 squared mod p to the 2b. Okay? We've killed off the 2, 3, 5, 6 variables. But the 2, 3, 5, 6 variables are important because they told us what scale to look at the quadratic equation at. Right? Okay, great. So what do I do next? Well, it's squares, so let's do difference of squares. What's the difference? Well, the difference is p to the b times a1 minus a4. And what's the sum? The sum is 2c plus p to the b times a1 plus a4. And we know that's divisible by p to the 2b. Right? Oops. Okay. So 2b copies of p must divide the left-hand side. Well, we have p powers here. We have b powers here. So that means the b powers of p must divide this multiplicative expression over here. Okay? Some of them could divide this guy, some of them could divide this guy. But we haven't used one last thing. We haven't used the fact that c is not divisible by p. So that means no powers of p can divide this guy. Right? Because c is not 0 mod p. So that means this thing is not divisible by p. So that means all the powers of p must divide this guy. So this implies that a1 is congruent to a4 mod p to the b. Right? This is the extra hidden congruence. This is where the efficient congruence gets its name. A priori, the n1s and n6, when I count this thing, there is no hidden conspiracy between them. But if I look carefully, there is this extra congruence that pops out between n1 and n4. Right? So how do we finish? So if I fix, how many choices of a4 are there? Well, there are p to the b many copies of a4. That's where this comes from. So fix p to the b choices of a4 mod p to the b. Then a1 is fixed mod p to the b. If I know what a1 and a4 are, mod p to the b, then I actually know what n1 and n4 are mod p to the 2b. Okay. Then I know that n1 is congruent to n4 is congruent to, let's say, some c prime mod p to the 2b. And there are p to the b many possible choices for c prime. And that's where we get 2b over here. And then for the 2, 3, 5, 6 variables, we do nothing. Right, we haven't upgraded them anything, so we keep them there. Okay? And then once you add in the notation, then you see that this is exactly what you want. Right. Great. So this is where efficient congruency gets its name. A priori, there's no hidden conspiracy between the N1s and N6s. When I plug in the residue classes, we see, aha, there's this extra expression over here that allows us to count efficiently. Right? This expression is sharp. If you normalize them by the correct amount, the left-hand side is 1, the right-hand side is 1. This is a sharp, this is the right estimate to do. Okay? So the P to the V loss is the exact right estimate you need to lose. Okay, great. So in the last 10 minutes, great. Now that you've seen this proof, what does this mean in Furry analysis? I mean, we're doing solution counting here, right? So we have to think about what we just did. Okay. So what was step 1? What was, broadly speaking, what's step 1? Step 1 was that we can assume that 4 of the variables are at the origin, right, using translation invariance. Okay? Step 2 was that these 4 variables dictate which scale to look at the quadratic equation at. They tell us to look at the quadratic equation at scale mod p to the 2b. And once we're there, we need to study we need to find some sort of diagonal behavior between N1 and N4. Right? What's diagonal behavior in harmonic analysis? This is Planck's relevant. Right? We need to find some sort of diagonal behavior between N1 and N4, and then we're done. Okay? So let me give a proof of the key estimate using this idea. Okay. And it won't be, I'll leave some of the details skipped because we've seen this proof like 3 times now. But just to illustrate the idea. Maybe I keep this up. Let's erase this one. Okay. So we now prove the key estimate for parabola decoupling using those ideas, number theory ideas, using efficient congruencing ideas. I mean, I guess the whole argument is an efficient congruencing idea, but what I personally believe is the closest proof of the key estimate to this argument. Okay. That most closely resembles efficient congruencing. Yeah. Okay, so what did we want to prove? Remember, the key estimate in the decoupling world was this. Okay, and then where I is of length nu to the, let's say b, I prime is of length nu to the b, and they're separated. And of course, f is for a transform supported in a delta square neighborhood of the parabola. And you can already see that this is going to be related, right? So what does this say? Keeping the 4 variables, 2, 3, 5, 6, the same on both sides, I gain nothing. I've decoupled 2 of the variables from, so n1 and n4, down to scale nu to the 2b, down to scale mod p to the 2b, right? This was originally, these 2 variables were at scale mod p to the b. They break down into mod p to the 2b. So like, afterwards, you see that, well, this is exactly the estimate you should prove. But of course, you only see this afterwards, right? Great. So let's follow the steps. What was step 1? Translate 4 of the variables down to the origin. Well, we can do that in harmonic analysis. That's parabolic rescaling. So I'm going to do something you can't do on paper. Well, so I can shift I prime to be at the origin. Okay, and that changes this problem so that, let's say I'm within nu away from the origin. Great. Now what was step 2? Step 2 says these 4 variables dictate which scale to study these remaining 2 variables. Okay, then now I have to think about, well, what does this mean? Well, we have the uncertainty principle. So f theta 0 nu to the b Okay, where is this supported? This is 0 nu to the b. Okay. These guys, well, what's the direction? This is vertical. Okay, so is essentially constant on vertical nu to the minus b by nu to the minus 2b rectangles. Okay, this is the right scales, the right objects to study this expression on. Right? This is the uncertainty principle. Okay, great. Great, so it suffices to show for each vertical nu to the minus b by nu to the minus 2b rectangle, we have that the integral over a rectangle this is now at the origin, we have this estimate. Because once we finish, we can sum over all the vertical, we just tile R2 by vertical rectangles of this size. We have this estimate on each of the rectangle, we sum, we get this estimate. Great, now let's use the uncertainty principle again. Well, on each of these boxes, f theta 0 nu to the b is constant on it, and it appears on both sides. So we could just cross it out. We're clearly making use of the uncertainty principle here, right? Like this is 5 on this box, and this is 5 on this box, so I can cancel it. Great. So now we just need to show that the integral of box okay. So we're at the stage where we these 4 variables told us to look at this equation sort of at some scale. Okay? And what more thing did it say? Well, it said to look at the second equation, the quadratic equation, at scale p to the 2b. So what does this mean? This means we should only look at in the y direction. Right? This is of x comma y squared dx dy. This is of x comma y squared dx dy. Right? Great. So let's freeze x and look at the y direction. Okay. Well, let's keep that here then. Okay, so let's first do something easy. So this is any square of size, any rectangle, nu to the minus b by nu to the minus 2b. Since f is arbitrary, you can assume that one of the endpoints is at the origin. Just translate your box. Okay, so without loss of generality, box 0 nu to the minus b by 0 nu to the minus 2b. Okay, so then suffices show, I'm being pretty pedantic, but let's get to a point. Okay. Okay. And then what did we say? Well, it said, well, okay, well, let's freeze x and look at the decoupling only in y. That's what this suggested. Only look at the quadratic equation. Okay, so suffices to show for each x naught and 0 nu to the minus b that the integral over 0 nu to the minus 2b f theta I of x naught y squared. I guess there's a loss here, is bounded by nu to the minus bounded, sum over j, dy. And then I claim that this follows from Plancherel, because so you can change these functions into indicator functions. Well, what's the Fourier transform of this guy? Well, that's an interval centered at the order of length nu to the 2b, right? So what's the picture now? So I have an interval I that's pretty far away from the origin. It's of distance nu. And nu is like delta to the epsilon, so you think I'm pretty much 1 away from the origin, right? And I'm only looking at the y support, so f theta I, and I partition f theta j's. So where's some red chalk? So each j down here lifts to a j, f theta j here, which has a vertical projection over here. Okay, so so if I start here, what's the length of this guy? Okay. Let's imagine for simplicity that I'm actually a distance 1 away from the origin. You can keep track of powers of nu, and that's exactly why you lose some powers of nu here. If I'm a distance 1 away from the origin, this is of length nu to the 2b. That means this guy is basically of height nu to the 2b. In other words, this length is of length nu to the 2b. Right? So what's happening is that I have these colors over here. That goes over here, that goes over here. And these intervals over here are of length nu to the 2b. So I'm basically saying I have these intervals of length nu to the 2b. I take this guy, I lift it over here, and then I project it to the y-axis. Are these almost orthogonal? Well, the answer is yes, because they're almost finite, they're only finitely overlapping. And so this follows from Plancherel after some effort. And well, that's exactly finding difference between n1 and n4, right? n1 and n4 are congruent mod p to the 2b. So, yeah. So this is the proof of the quiescent that I personally think is the closest to this argument over here, right? So step 1, you shift to the origin. That's exactly what happens. And the 4 variables tell us which scale to look at the other 2 variables. Well, they tell us to look at these scales of size nu to the minus b by nu to the minus 2b. Then they also tell us to look at the quadratic equation. Well, let's only look at the direction and the y. Okay. And then they tell us to find diagonal behavior. So we should apply Plancherel. Right? And a similar type argument is sort of what we do, what I do with Polemyang, Xiaomengguo, and Pavel Kozorin-Krennis when we translated Woolley's 2017 efficient cognitive theorem into decoupling for the moment curve. We gave a very different proof a much shorter proof of decoupling for the moment curve. Yeah. So I've now given you 3 different proofs of this estimate in all sorts of styles. Sort of the easiest sort of follows from Plancherel style. And then in the very first proof that I gave, you can still see images, glimpses of this. And then I gave you a proof that in the style of Borg and Demeter, and then I gave you a proof that I'd say is closest to the short proof of the moment curve that I have. So hopefully you're satisfied. There's, I think, one more proof where you can actually use the fact that these are 2 and 4, and you can expand everything, but that's the most classical and the hardest to generalize. But anyways, that's all I have for today. So yeah, are there any questions?
And so you mentioned the proof for again first time, the proof for any case.
Mm-hmm.
And you mentioned the proof for any case, the proof are very different.
So in the when k, let's talk about when k equals 3. So the curve is c comma c squared comma c cubed, right? And the critical exponent is L2, L12. Okay. So this style of proof, what will happen is that you will actually create two bilinear constants. You'll create one that has a 2 plus 10. The 10 is not important. Just like here, the 10 is, we did not use the 4, right? The 4 was only like, you know, it didn't matter that this was an integer. You could be like pi for all that matters, right? So the 10 is not important, the 2 is, so the 2, so there's a bilinear constant that looks like this, and the 2 is going to be exactly the same proof. This uses line decoupling, Plancherel. And there's going to be a second bilinear decoupling constant with a 6 and a 6. This 6 is also not important. The 6 is because it's only 12 minus 6. This 6 is important because we're going to make use of L2, L6 decoupling for the parabola. The idea being that the following. So I give you three equations here. In the number theory world, I give you three equations, linear, quadratic, cubic. Okay? I tell you, you're only allowed to pick one equation. Okay, which one do you pick? Well, you should pick the cubic equation because that has the most algebraic data. Right? And that's sort of what's used here. Okay? And what's used here, right? Why in this argument did I pick the quadratic equation rather than the linear equation? Well, the quadratic equation is the one that gives the most data. Right? If I told you, take quadratic Venerata, you have linear and quadratic. You're only allowed to pick one equation. Which one do you pick? Well, you pick the quadratic one. Right? That gives the strongest residue class restriction. Right? So similarly, here, if I'm only allowing you to pick one equation, you pick the cubic equation. Okay, then there's a bilinear constant for this guy. And then for this guy, I'm allowing you to pick two equations. Which two do you pick? Well, you should pick the quadratic and cubic one because that gives the most algebraic data. Like that makes sense most algebraically because that should give, picking these two equations should give way more restrictions than just picking the linear and quadratic restriction. Right? And of course in degree k, right, so what do you do when, let's do k equals 4. K equals 4, you want to do L2, L20 for the moment curve c squared, c cubed, c to the 4. Okay, so what do? Well, you pick one that has 2 plus 18. Right, this is one. If you have four equations, pick one. Okay, you pick the fourth power. You have another one that uses L2, so this is line, lower dimensional data. You have one that deals with parabola, lower dimensional data. And you have another that deals with the cubic moment curve. So the cubic moment is 12. So this is cubic moment curve, lower dimensional. And you have three sort of bilinear constants that all interact with each other. And here you want to use Plancherel. Here you want to use L2, L6 parabola. Here you want to use L2, L12 cubic moment curve, and they all interact with each other and miraculously work. So this is the style in the Woolley's nested efficient congruencing argument. In the Bourgain-Demeter argument, they will use one sort of, in this case it'd be like L, you'd have something like each one is like the fifth power or something like that, and you'd have one multilinear constant. Yeah. So, yeah, this type of argument was written out. The iteration was mostly, this type of argument was written out in the short proof of the moment curve by Xiaoming, Polem, Pavel, and myself. Of course, the iteration is basically due to Woolley. The iteration is very clean. What happens is that you get this giant matrix that turns out to be a Markov matrix, and it's very obvious that it has eigenvalue 1, so it's clear once you write out the matrix, you win. Yeah. Yeah. So, yeah. Okay. Are there any other questions? Okay.
Thank you very much.
Okay.
So maybe just a quick announcement, right? So next week there's no lecture because then it's unavailable. And he said that certainly he can deliver the lecture online, but I think we prefer maybe to go to person.
Yeah.
So probably the next week lecture is postponed to maybe 2 weeks or 3 weeks.
Yeah.